All right, these are the mechanical energy slides. So the first two, just to review energy. Energy is the capacity to do work. All forms of energy are scalar, which means only magnitude, no direction. And the unit for all forms of energy is the Newton meter, also known as the joule. So there are four basic ways of storing energy: potential energy, kinetic energy, internal energy, and rest mass. And these are broken up into different categories as well. So if we ask this question, what can energy do that momentum cannot? Well, that brings us to the law of conservation of energy. So, like momentum, energy cannot be created or destroyed. It can be transferred from one place to another, just like momentum. However, energy differs because there are different forms of energy that energy can transform and change into, but momentum cannot because there's no other forms of momentum. So, I compare energy to traveling to a different country. The first thing you have to do is exchange your money. Now, you're not getting any richer or poorer by doing that. You still have the same buying power, you just have a different form of currency. So then we revisited elastic collisions, and we looked at elastic collisions. And during an elastic collision, in terms of energy, what happens is kinetic energy is conserved. So all kinetic energy gets transformed into kinetic energy. It just transfers to different places. No energy is lost to the outside world due to internal friction. Now, in elastic collisions, some of that kinetic energy is transformed and changed into other forms of energy. So that's why all collisions have some inelastic collision properties, because some of that energy is lost to the outside world. So what is mechanical energy now? Now, mechanical energy is the energy due to the position of something or the movement of something. So the three forms of mechanical energy are kinetic energy, which is the movement of something, and there are two forms of potential mechanical energy. You have gravitational potential energy, that's energy at a height, and elastic potential energy. That's energy like being stored in the material when it's being stretched or compressed. So potential energy is the stored capacity to do work due to its location in a force field. Now, the three forms of mechanical energy have these equations. So this is gravitational potential energy, we have elastic potential energy, and kinetic energy. And to find the total mechanical energy of an object, we just add all three of those mechanical energies together. So mechanical energies can be transformed into other forms of mechanical energies. In an isolated system, if there's no losses to friction and no forces from the outside, then we say that the total mechanical energy of the system is conserved. So a roller coaster is a good example of this. Now, the total mechanical energy of a system, that means the sum of the kinetic energy, gravitational potential energy, and elastic potential energy of the objects in that system. We're not including chemical potential energy, internal energy, rest mass, energy lost to heat, sound, light, etc. Right? So you can see that equation there. This will get us that object's energy of its either motion or position. So we explored this in the Popper lab. So the Popper lab is just bending back a little toy, setting it on the table, and it pops up. Now, we were able to calculate the gravitational potential energy by finding the height that that popper went to. We needed to know the mass as well and the strength of the gravitational field on Earth. So when we did that, assuming the maximum height the popper reaches is at rest, not bent back, calculate the mechanical energy at its maximum height. Well, at the very peak, the mechanical energy is all gravitational potential energy. That's where all of that mechanical energy is. Now, then this next question asks you to find the elastic potential energy. Well, you don't have to use that equation, because if we know that energy is conserved, cannot be created, cannot be destroyed. Well, if I know my total mechanical energy at the peak, well, all of that mechanical energy is now elastic potential energy when it's bent back sitting on the table. And the instant it pops, it's all going to be kinetic energy. So all of that elastic potential energy was transformed into kinetic energy. So those all have the same answers, right? You find the gravitational potential energy at the very peak. Well, that's all the mechanical energy. All that mechanical energy is elastic potential energy when it's bent back sitting on the table. And the instant it pops, it starts to it converts it into kinetic energy. So those are these conclusion questions here. At the very peak, it's not moving, not bent back. It only has gravitational potential energy. Well, when it's bent back sitting on the table, then or when it's bent back sitting on the table, it's all elastic potential energy. The instant it pops, it's all kinetic energy. As it's moving up, well, it does have a height, so it does have some gravitational potential energy, but it also is moving, so it has kinetic energy. Now, at the very peak, at the maximum height, it's going to be It's going to be all gravitational potential energy. And the popper is going to be moving the fastest when it has the most kinetic energy. That's the instant it pops. So throughout this, all that mechanical energy is just transforming into other forms of mechanical energy, right? No energy was created or destroyed. All that energy was elastic potential energy. It pops. It's all converted into kinetic energy. As it's moving upward, that kinetic energy is being converted into gravitational potential energy. At the peak, it's all gravitational potential energy. That's what's happening in this lab. So now let's answer this question, though. What happens to an object's kinetic energy and gravitational potential energy as it falls? So if we look at this lab, Energy Skate Park, in which the skater's moving up and down, you were to match the pie charts to what was happening in that lab. So these are the answers to that. So this is what we got for that. And the green represents kinetic energy, blue represents gravitational potential energy. So you'll notice that points A and F are the same. Well, if we look at the gravitational potential energy equation, well, they have the same height. So they're going to have the same gravitational potential energy. Now let's look at points B and E. Well, they're the same. They're across from each other. They're at the same height. So they're going to have the same gravitational potential energy, and they're going to have the same kinetic energy. So you can't see it on here, but the bar graph that represented total does not change because it's just the potential energy and kinetic energy added together, and that's not going to be created or destroyed. So what's happening to the mechanical energy of the skater as she's going up and down the ramp? Well, as she's going down, that gravitational potential energy is being converted into kinetic energy. And as she's moving up, that kinetic energy is being transformed into gravitational potential energy. Now, when is the skater moving the fastest? Well, she's going to be moving the fastest when she has the most kinetic energy. So that would be down at the bottom, point C, because all that gravitational potential energy was converted or transformed into kinetic energy. That's where all the mechanical energy is. So then you can calculate how fast she's going, because if you know the gravitational potential energy at the top, all of that gravitational potential energy was transformed into kinetic energy. So then you can use that equation if you know the mass and gravitational strength. All right, so now how can mechanical energy be used to gain an advantage at the carnival game Roller Bowler? So that brings us to the over the hill lab. So if we look at this, you're trying to place the marble on point A, you're trying to push that marble, go over the hill, over point B, back down to the valley, up the ramp, point D, and then back down to rest in the valley so it doesn't go back over the hill. So if we look at the picture, the mechanical energy, well, at point A on the straightaway, once it's moving, it has all kinetic energy. It's not at a height. Well, now as it's moving over point B, moving over the hill, it's going to have, well, it's moving, so it has kinetic energy, but it's also at a height. So some of that kinetic energy was transformed into gravitational potential energy as well. Now, at point C, well, that gravitational potential energy was transformed back into kinetic energy. So at point C, it has all kinetic energy. And once it comes to rest on the ramp at point D, then it has all gravitational potential energy. Now, if we look at these questions, what must be true about these conditions in the track in order to get it to rest at point C in the valley? Well, the ramp has to be taller than the hill, right? Point D has to be taller than point B because all of that mechanical energy has to be transformed into gravitational potential energy. If there's any kinetic energy left over, it's going to fly right off the ramp. So assuming no energy lost to friction or internal energy, what can be said about the velocity of the marble and straightaway and the valley, point A and point C, if they're at the same height? Well, if they're at the same height, they have the same gravitational potential energy, which means they have the same kinetic energy. So they're going the same velocity. Now, once the marble is pushed, it's going to have a velocity on the straightaway. How could a velocity be calculated to ensure the marble would make it over the hill but not launch off the ramp? So this is trying to find the sweet spot of how much kinetic energy has to be given to that marble in order to get it over the hill but not launch off the ramp. So if you put that marble on top of the hill and it has 10 joules of gravitational potential energy, you have to give that marble at least 10 joules of kinetic energy so it can be converted into gravitational potential energy with some left over to move over the hill. Now, let's just say you put that marble on top of the ramp at point D, and it has 12 joules of gravitational potential energy. Well, if at point A you give it any more than 12 joules of kinetic energy, it's going to have a little bit left over, and it's going to little bit kinetic energy left over once it gets to the end of that ramp, and it's going to roll off the ramp. So it has to be somewhere in between those. But it has to be, the kinetic energy has to be in between the gravitational potential energy of the marble at top of point B and the gravitational potential energy of that marble at the top of point D, that ramp. Now, would it even be possible to push the marble? Like, would this be possible if we don't lose any of that heat? Well, the answer is no, because what happens is as it's moving over point B, it's over that hill, it's going to have some kinetic energy. Well, if that energy isn't shed, like due to friction, heat, sound, then it's going to have kinetic energy coming back and it's going to roll back. So in order to accomplish this, to get it stuck in the valley at point C, there does have to be some losses to the outside world. So if we look at a roller coaster, right? At what point on the track is the marble going the fastest? Well, it's going to be at the lowest point. So C and E, well, they're going to be going the same speed. Now, at what point on the track is the marble going the slowest? Well, it's going to be at point A, at the highest point. That's where most of that energy is gravitational potential energy. At what 2 points on the track is the marble going the same speed? C and E, because they're at the same height. So rank the points along the track, the marble going fastest to slowest. How did you come to this answer? So we're just going from the bottom to the top. C and E are going the fastest because they're at the lowest point. They're going the same speed. Then it goes D, then B, and then A, it's going the slowest. So without any external forces, will the marble be able to go higher than point A? Why or why not? Well, no, because that's where all the mechanical energy is. If it starts at rest, that's all that mechanical energy. So if we look at a pendulum, at what point along the path is the pendulum going the fastest? It's going to be down at the very bottom, because that's where all that mechanical energy is kinetic energy. When is it going the slowest? Well, it's when it reaches the peak. So rank the points along the pendulum, slowest to fastest. So if they were given a problem, you just look from the bottom up to the top, or no, sorry, top to bottom. So slowest is at the top, fastest is at the bottom. Now, without any external forces, will the pendulum ever go higher than point D? So will it ever go farther than that point that it started at? And the answer is no, because energy cannot be created or destroyed. So that brings us to the question, do you trust the laws of physics? So that brings us, if you set a bowling ball right next to your face and you let it go, well, there is going to be some energy lost to like friction, to air, like the wind resistance. So it will not return to the original height and you'll be safe. All right, so just as a final thought, remember there's too much unknown in the universe to take a break from learning. Get out there and question everything.